Hey everyone, welcome back to the CIE A-Levels Physics series. Today we're going to talk about the paper 2 of the February-March 2025 exams. Before we dive into this paper, some resources that are going to be valuable for you, we have neatly packed them in this Grade Booster pack available on our Patreon, which the link for which we will give in the description, but just to show you what's included inside. For AS and A2, the resources are kept slightly separate. They include definitions and formulae, just to show you what it includes. All of the important definitions and facts and formulae are included in the AS definitions and formulae. Then we have uh, important derivations that are often examined in the exams and the ones required by the syllabus. Frequently examined questions up till now, they include only the paper 2 ones, but soon we will be adding the paper 1 questions also, since this is AS. Then we have the A2 or the A-level physics. This is the graphs. We know we all struggle with the field graphs, the gravitational and the electric field. So we have got you covered. Here you will see the graphs, their equations, and how to plot them. Similarly, we have definitions and formulae for A2 also. Similar document with definitions, formulae, and some key figures. Important derivations for A2. We know how important we have derivations for us. Some derivations are very frequently examined for A2, and last but not the least, frequently examined questions for A2. Uh, this is very updated, so we have included um, all the recent and the very frequent examined questions. On the left hand side, you can see that this is the syllabus. The second column is the question, third column are the answers. These answers are marking scheme aligned, so you don't have to worry about anything. The rightmost column is the year. If you do not find a year written with this does not mean that they are not examined questions or frequently examined. They are just interesting ones. And as you can see, there are going to be some questions that have a lot of years written with them, so that means that they are very important ones. So for example, you can see this over here. All right, one more thing. We have also included this paper 5 planning question, which is the question number 1 checklist over here. This is basically a very neat little checklist. And after this, we have some example questions. The diagrams I've already drawn for you, some example experimental uh, data that you can write in the exam. For example, as you can see this over here, this is October, November 2024, 5.2, variables, apparatus, and setup, how you can draw this, the experimental methodology that you can try to understand and copy. Not like exactly copy, but you can get the sense of what to include, what is important, the procedure, the data table, the analysis, and the safety considerations. All of these are uh, going to be very helpful for you. Now, going back to this paper that we want to see. All right, let's start with the first question. Explain what is meant by accuracy of a measured value. Just to show you how much we have thought about this, these little things are included in these documents, in these grade booster packs. So for example, we are looking for accuracy. It's a measure of how closely the average of multiple measurements agrees with the true value of the physical quantity. Now, we are not talking about the multiple measurements over here yet. So you can skip this part out. So how closely the measurement agrees with the true value, or measurement agrees with the true value of a physical quantity. So we can actually write like that. So we can say that it is the measure of how close the measured value is to the true value of the physical quantity. All right. Two solid cubes A and B are measured to determine the density of their materials. Table 1.1 shows the measurements for cube A. We have length and mass. As you can notice, we have centimeter and grams. However, the question showed that the calculated density of material of cube is, this is written in kilograms per meter. So that means we need to convert these values into meters and kilograms. So 1.53 centimeter converts to basically 1.53 10 raised to power minus 2 meters. This is already 31.3, so 31.3 grams when we convert this into kilograms. So 31.3 divided by 1000. As you can see, we will get 3.13 10 raised to power minus 2 kilograms. The percentage uncertainty or the fractional uncertainty is not changed by this change in the units. So we don't have to worry about that. All right, if we need to find out the density, we know that the volume of cube would be length cubed. So basically length is 1.53 10 raised to power minus 2 whole cubed. So that would be 1.53 cubed 10 raised to power minus 6. So all we have to do is do 1.53 this. So this would be 3.581 10 raised to power minus 6 meter cube. Intermediate values, we can keep a higher number of significant figures in decimal places. Density is mass over volume. So mass is this 3.13 10 raised to power minus 2 kgs. Volume we have already calculated, 581 10 raised to power minus 6 meter cube. Let's see what we get. Let's save this. So we have 3.13 divided by the answer value that we had. Now times by 10 raised to power minus 2 plus 6, we will get 8.739, and to two significant figures it would be 8.7. 10 raised to power 3 kilograms per meter cubed. Right, calculate the percentage uncertainty in the density of the material of the cube. Okay, so we know that the percentage uncertainty in the length, or the fractional one for now, this can stay as this value because the percentage or the fractional uncertainty is not affected by changing of the units. Similarly, we have the mass. This would be 0.5 over 31.3. However, we have volume also. Volume would be, since volume is L cubed, so we would do 3 times by 0.01 over 1.53. Now we need the percentage uncertainty in the density. So we would have sigma rho over rho. We just have to add these values. First, these are the fractional ones, so be very careful. We have to multiply by 100 at the end, 31.3 plus 3 times by 0.01, that is 0.03 divided by 1.53. So first let's calculate this value divided by 31.3 plus 0.03 divided by 1.53. This is the value. So 3.558 10 raised to power minus 2. And then when we multiply this by 100 to get a percentage, this would be 3.558%, so roughly 4%. Okay. The density of the material of QB is determined to be 9.2 10 raised to power 3 plus minus 6%. State and explain whether cube A and cube B could be made from the same material. Now, how we can actually do this is by working out the range of the values that we have for A and B. So let's write somewhere else. Let's write on the right side over here. So we have 8.7 10 raised to, for A, we have 8.7 10 raised to power 3 plus minus 4%. And for B, we have 9.2 10 raised to power 3 plus minus 6%. All we have to see is where the range are. So density of A, so let's see, 8.7 10 raised to power 3, sorry, to 3. The lower end 1 minus 4%, this would be 8.352. We just need the numbers because the powers are the same, 10 raised to power 3. Then we can try out with a plus 9.048 10 raised to power 3. Then we need the same thing for the 9.2. So 9.2, and this is 6%. So the upper value is 9.752 10 raised to power 3 density of B, and we have minus 8.648 10 raised to power 3. So if you draw this on the number line over here, show this over here, so 352 is a little bit over here, 352, 648, and 9.048 and 9.752. So for the A, let's use this blue one over here. So this is in between this value. Oh, sorry, no. Doesn't matter, we just, doesn't matter the exact sign, we just need the general idea of this. And this one goes from this value. So there is definitely some overlap in this region. So there is definitely some overlap. So this means that this could be made from the same material. So there is a major overlap in the values. Okay. So there is overlap in the ranges of densities of cubes A and B. So so A and B could be made from the same material. That's it. All right, moving on. State the principle of moments. Okay, so just to show you uh, principle of moments. This is in force chapter, force density chapter. Principle of moments. Sorry, where did this go? Oh, sorry, I think it should be in this one then. Yeah, principle of moment states that for a body to be in equilibrium, the sum of the clockwise moments about any point must be equal to the sum of anti-clockwise moments about the same points. That's it. We can say that the sum of anti-clockwise moments about a point should be equal to clockwise moments about the same point. And when does this apply? For a body in equilibrium. For a body in equilibrium. Or rotational equilibrium, you could also say. So basically, for a body to be in equilibrium, or rotational equilibrium also. Okay, a solid plastic cylinder floats in water. It is used to support one end of a horizontal uniform beam as shown. It is used to support one end. Oh, okay, this one, sorry. This is the cylinder. It is used to support this end. The other end is connected to a hinge. Okay. Beam has a length 6 meters and weight 1700. And since this is uniform, that means the weight of the beam will act at its midpoint at exactly 3 meters over here. So at exactly 3 meters over here, center of gravity will be over at this point. Okay. Beam is attached to solid ground with a hinge at A. Cylinder is floating vertically in water. The top of the cylinder is attached at its center to the beam at a horizontal distance of 5 meters from end A. The cylinder applies a vertical force of 1300 Newton to the beam. A person of weight 660 Newton stands on the beam at point P. Okay. Beam AB is in equilibrium. Okay. By taking the moments about A, determine the distance x from A to P. Okay, so we have to apply these principle of moments. Since this system is in equilibrium, we have to apply anti-clockwise moments equals to clockwise moments. So counterclockwise, you can anti-clockwise moments is equal to clockwise moments. So anti-clockwise moments are this one. This is 1300 at 5 meters. Are there any more? No, no. Now the clockwise moment, the one is the weight of the beam and the other is the weight of the person. So sorry, we have 660 at x plus 1700, yeah, 1700 at 3 meters from A. Right, so 1300 times by 5 is 6500. 660x plus 17 times by 1700 times by 3, that is 5100. So all we have to do to find out x is 6500 minus 5100 divided by 660. So we have 6500 minus 5100 divided by 660. This is 2.12 or 2.1 meters. Okay, so now moving forward, the bottom of the cylinder is submerged in the water to a depth y as shown. This is y. The beam is still attached to the cylinder but not shown. Cylinder has mass 11 kg, diameter 0.78 meters. Beam exerts a vertical force of 1300 Newton on the cylinder. This is shown over here. Cylinder is in equilibrium, that means the forces are balanced. Show that the upthrust acting on the cylinder is 1400 newtons. Okay, how we can know that? So this is the upthrust acting upwards. We have weight acting downwards and the 1300 Newton force. So these forces are balanced. So so we have upthrust equals to 1300 plus 11 times by 9.81. So let's see. So 1300 plus 11 times by 9.81, we have 1407.91, approximately equal to 1400 newtons. Now, the water has density 990 kg per meter cubed. Calculate the depth y. So this is related to the upthrust. So upthrust is equal to rho g v. This v, however, is not the volume of the entire cylinder. It just includes those volume that is submerged. So v is the volume that is submerged, or better term for that is volume displaced. So density is 990, G is 9.81, and volume, for volume of cylindrical objects, we have area times by length. Since it is a prism, area is given to us as, no, we don't have area, we have diameter. Okay, so area is pi, diameter is given as 0.78 whole squared divided by 4, and length is given as y. So we can just simply write over here. So 1400 is equal to pi by 4, 0.78 whole squared times by y. We just need to find out y now. So answer divided by 990 divided by 9.81 times by 4 divided by pi divided by 0.78 whole squared. So we get y equals to 0.301, which basically means just 0.3 meters. All right, moving forward. The person can stand anywhere between A and B. On figure 2.3, sketch the variation of the depth of the bottom of the cylinder with the distance of the person from A. For the distances between 0 to 6, numerical values are not required. To understand this sketch over here, we have to go at this thing. So if we just simply rearrange the formula for y, so we have upthrust. Upthrust we found from we had 1300. This 1300 will change as the person moves on the plane, on the plank. So what we do over here, let's use 1300. Let's say this is our x. So upthrust is just simply x plus 11g, which is a constant. This is a weight of the that will remain the same. And then we have the 990 g times by the volume, and volume is cross-sectional area, that is just simply pi 0.78 whole squared over 4 times by y. Now, as you can see over here, y depends on x. So you just equate these together. So y depends on x linearly. So it's not a proportional relationship, but it's still a straight line relationship. So when you take everything on one side, when you take this entire thing on the other side, you will have y equals to this bracket, 1 divided by this entire bracket, times by x plus 11g. So this is a straight line relationship. And what it appears to be is that it's going to be a positive gradient because there is no minus happening over here. So there is no minus. So the gradient component of this would remain positive. So this would go like this. So remember, it's not going to be 0. So it's not going to be 0. All right, moving forward. A truck R of mass 9400 kg moves with a constant acceleration in a straight line down the slope, as illustrated. At point A, the speed of the truck is 13 meters per second, and at the point B, the speed of the truck is 22. A and B are a distance of 180 meters apart. Calculate the acceleration of the truck between A and B. Okay, so we just have to use the kinematics over here. So remember, we do not have the time, so we can't use the v minus u over t. What we can use is 2as v squared minus u squared. So acceleration would be v squared minus u squared over 2s. So v is 22, u is 13, and 2 times by 180. Oh no, sorry, the automatic shapes were on. So all right, so 22 squared minus 13 whole squared, 315, divided by 360, 2 times by 180. So that is 0.875 meters per second squared. So we can just write it in two significant figures, 0.88. Determine the gain in kinetic energy of the truck between A and B. So simply we can just do half mv squared minus half mu squared. So change in kinetic energy would be half mv squared minus u squared. So half m is 9400 times by 22 squared minus 13 squared. So 9400 divided by 2 times by, wait, sorry, we can start by doing 22 squared minus 13 squared first, and then times by 9400 divided by 2. So we get this value. If we write this in the standard form, we will get 1.5 10 raised to power 6 joules. Okay. A short time after passing point B, the truck R moves in a straight line on a horizontal ground. The driver of the truck applies the brakes. Figure 3.2 shows the variation of the time of the momentum of the truck. Okay, define force. It's easy. This is rate of change of momentum. This is also available in the definitions and formulae document. Show that the average resultant force acting on truck R between the time t is equal to 0 and time t is equal to 15 seconds is minus 1.2. So we just need average resultant force. So basically what we can do is we can draw a line connecting these 2 points. They're not asking for instantaneous, they're asking for average. So this connected, oh no, right? And one more thing that we can do, we can, okay, never mind. All right, now we need the values. So this would be 0 and, oh, we first have to see what the values are. So 5 is distributed between 10. So this means that this is 0.5. This value per small grid. So this means that this is going to be 21. And this value on the other hand, sorry, this value, this would be 2.5. Right, okay. Right, so 21. So average force would be the gradient, simply average gradient. So we have 21 minus 2.5, 10 raised to power, what was the value? Oh no, 10 raised to power 4 divided by 15 seconds. So we have 21 minus 2.5 times by 10 raised to power 4 divided by 15. We get this value. So 1.23 recurring, times by 10 raised to power 4 newtons. Now, since this was decelerating, we will have a minus thing. So this is actually 0 minus thing. So this would come out to be minus anyway. So we can just simply write it as minus 1.2 10 raised to power 4. Okay. An identical truck S has the same initial momentum as truck R. Truck S experiences a constant force equal to the force F in B. State and explain whether truck S will take more or less or the same amount of time to come to rest as truck R. So if they have the same momentum, initial momentum, and it is experiencing a constant force equal to this stopping force, you could say, or braking force, or resistive force also. Either way, whatever this is causing deceleration. State and explain whether truck S will take more, less, or the same amount of time to come to rest as truck R. Okay, so the key word over here is this is a constant force. But on the R, it was a non-linear force. So basically, what's happening over here, let's say this is for S, this is for R, this is R, and this is now S. So the total change in momentum would be the same, right? But it's coming to rest according to the same thing, since if they're starting at the same initial momentum and it's experiencing the same force rate of change of momentum, that means it will follow this blue line and it will come to rest at, let's say, somewhere between like 17.5 or 17, I guess. So let's say this is 17.5, either way. So it will come to rest at this point, but this is coming to rest at 21, 22, and 23. Yeah, so since it is experiencing a constant force, it will come to rest faster. So that is the entire point over here. So the total change in momentum may be the same, but since S is experiencing a constant force, not a non-linear force, non-uniform force, its momentum is going to decrease linearly, and it will come to stop at 17.5 or roughly 17, whatever you want to call it. So this is what we will write over here, that since S is experiencing experiences a constant force, meaning uniform decrease in momentum, unlike R, it would come to rest earlier than R. We can use the numbers also. R comes to rest at 23 seconds, but S would come to rest at around 17 or 17.5 seconds if uh, rate of change of momentum or change in momentum is extrapolated. If extrapolated. That's it. That's it. All right, moving on. A device containing a microwave emitter and receiver is placed in front of a large metal sheet in a vacuum. The line XY is perpendicular to the metal sheet. The device emits microwaves of frequency 6.3 GHz. When the device is at position P, a stationary wave is formed between the device and the sheet. Explain how the stationary wave, including the nodes and antinodes, are formed. Now, this is very interesting, and let me show you how to answer this. So this is the same grade booster, but the frequently examined questions. So this is a similar question using the principle of superposition to explain the formation of a stationary wave. So if you notice over here, we have a stationary wave is formed by the superposition of two progressive waves of same frequency and amplitude traveling in opposite directions. They interfere constructively and destructively, producing regions of maximum and minimum amplitudes called nodes and antinodes, respectively. So that's all there is to it. So that's all we have to write. So, but we have to adapt to this particular scenario also. So when microwave is reflected at the sheet, it causes two waves, original direction, original and reflected, what is going on? To interfere or superpose, you could say. So again, you can use the word superpose also. Superpose or interfere with each other. This causes or this produces regions of maximum amplitude called antinodes and regions of minimum amplitude called nodes. That's it. So the points that were included is that the microwave is reflected at the sheet. It causes two waves to superpose or interfere with each other, produces regions of maximum amplitudes, antinodes, regions of minimum amplitudes called nodes. Calculate the wavelength of the microwaves. Okay, so since microwave is traveling at the speed of light, they have given us the frequency. So wavelength would be speed over frequency. Speed is 310 raised to power 8. Frequency is, sorry, I forgot again, 6.3 gigahertz. Giga is 9. So 3 divided by 6.3 times y, 10 raised to power 8 minus 9. This gives us 4.761 10 raised to power minus 2. So 4.8 10 raised to power minus 2. Now, at point P, the receiver detects a maximum amplitude of the stationary wave. So again, we said maximum amplitude means antinode. So this is the place of antinode. Okay, all right. Let's carry on. And at the point of reflection over here, this would be a node over here. Now, let's see. The device is moved slowly from point P along the XY, and the receiver detects a series of minimum and maximum amplitudes. First time a minimum amplitude is detected by the receiver is when the device is at point Q. So at this point, there is another antinode. Wait, just to confirm, this was oh no, sorry, this is a minimum amplitude. Okay, sorry, this is the minimum amplitude. So this is antinode. Sorry, node. So this is node. Now we know the distance between node to node or antinode to antinode is lambda by 2. Difference between or distance between antinode to node is lambda by 4. So this is all we have to do first. So node to antinode is equal to lambda by 4. So that would be, we have found the wavelength 4.761 10 raised to power minus 2 divided by 4. So this divided by 4, we get 1.2 10 raised to power minus 2. Okay. The intensity of the microwaves emitted by the device is increased. Frequency of the microwaves is unchanged. The device is moved slowly along the line XY from point Q until the next maximum amplitude is detected at point R. Where is R? We don't know where R is. Okay, where R is. Okay. State and explain whether the distance QR is greater, less than, or same as the distance PQ. So this is easy since the wavelength, since neither the wavelength is changing nor the frequency is changing, so the distance QR would remain the same. So this distance does not depend on the intensity. Distance between nodes and antinodes, or in short wavelength, if wavelength is affected, distance between nodes and antinodes will affect also. Does not depend on intensity of the wave. Therefore, QR will be the same as PQ. That's it. All right, so let's see question number 5. A stationary loudspeaker emits a sound of constant frequency. A microphone is placed near to the loudspeaker and connected to the cathode ray oscilloscope. The trace on the screen of CRO is shown. Okay. The time base of the CRO is set to 5 10 raised to the power minus 4 seconds per centimeter. Speed of the sound emitted by the loudspeaker is 330. Determine the wavelength of the sound. So for the wavelength, we need speed divided by frequency, or speed multiplied by time period. So time period, which we can calculate from the this. All we have to do is to figure out the distance between uh, between the points that are in phase, basically. So if this point is in phase, this point is in phase, this point is in phase with this point. So if we can figure out the time over here, so this would be 1, 2, 3, 4, 5, and 5.8, you could say. Let's check over here also. So yeah, so 1, 2, 3, sorry, 3, 4, 5, and it's 5.8. So again, 1, 2, 3, 4, 5, and 5.8. 6 would be over here, so this is just 5.8. 5.8, right. So time period would be 5.8 times by 5 10 raised to power minus 4. So 5 10 5.8 times by 10 raised to power minus 4. Now this times by the speed 330, this would be the wavelength, this would be 0.957, so 0.96. Right. Okay. The loudspeaker now moves in a straight line while emitting the same sound of constant frequency. The period of the trace on the CRO increases continuously. Describe the motion of the loudspeaker. So basically what's happening is the Doppler effect. So we can say, since the time period is increasing, the frequency is decreasing. Which means that the loudspeaker is moving away from microphone at an increasing speed, or with an increasing speed. You could also say accelerating. So the key word over here is that it is increasing continuously. So if it is continuously increasing, frequency is decreasing, ing, not decrease and then just stop. It is continuously decreasing, so that means it is gaining speed. All right, question number 6. A cylindrical copper wire of length 0.24 meters is shown in figure 6.1. The current in the wire is 0.85 ampere. Resistance of the wire is 3.3 milliohms. the total number of charge carriers N in the wires is 2.6 10 raised to the power 22. Resistivity of the copper is 1.8 10 raised to the power minus 8. Calculate the potential difference between the two ends of the wire. Okay, so we need for potential difference, we need I times by R. So current that is flowing is 0.85, and for resistance we need resistivity L over A. So resistivity is given as 1.8 10 raised to the power minus 8. Length is given as 0.24, and the cross-sectional area that is given to us, is it given to us? Oh, resistance of the wire. Oh, resistance is given. Sorry, my bad. Resistance is given. So this is 3.3 milliohms. So 0.85 times by 3.3, 10 raised to the power minus 3. So this is 0.003. You could write this in the standard form also. Show that the cross-sectional area of the wire is this. Okay, so actually we could reuse this. So R is equal to rho L over A, which means A is rho L over resistance. So rho is given to us as 1.8 10 raised to the power minus 8. Length, wait, sorry, again I forgot. Oh, length is given 0.24 divided by resistance that is given to us as 3.3 10 raised to the power minus 3. So 1.8 times by 0.24 divided by 3.3 times by 10 raised to the power minus 8 plus 3. So we get 1.3 10 raised to the power minus 6 meters squared. Show that the number of density of the charge carriers on the wire is this. Okay, so number density is equal to number of charge carriers divided by the volume. So first off, we need to find out the volume. So volume is equal to cross-sectional area times by length. So 1.3 10 raised to the power minus 6 times by 0.24. So this times by 0.24 is this 3.142 10 raised to the power minus 7 meter cubed. So N would be total number of charge carriers is 2.6 10 raised to the power 22 divided by 3.142 10 raised to the power minus 7. So divided by 3.142. Oh, wait, sorry. The answer that we had was this. Oh, sorry. Damn it. Okay, never mind. So 2.6 divided by 3.142 times by 10 raised to the power 22 plus 7. This is 8.3 10 raised to the power 28 meter per meter cubed. Now calculate the average drift speed of the charge carriers and the electrons in the wire. So we have I is equal to NAQV. So V would be equal to I over NAQ. So I was 0.85, and we have found to be 8.3 10 raised to the power 28. cross-sectional area we found to be 1.310 raised to power minus 6, and fundamental charge is 1.610 raised to power minus 19 coulombs. So 0.85 divided by 8.3 divided by 1.3 divided by 1.6 times 10 raised to power minus 28 plus 6 plus 19. So we get 4.910 raised to power minus 5. A different copper wire Q has the same volume as wire P but non-uniform radius. The radius at end X of the wire Q is same as the radius of wire P. Radius R2 is less than R1. State and explain how the resistance of the wire compares with the resistance of wire P. Now, how do we diagnose this? So this diameter or this cross-sectional area is the same as the one previous wire P, but this one is obviously lesser. So cross-sectional area has reduced. So what does that mean? So that means the average cross-sectional area, since it is, you can say, uniformly decreasing, or diameter you could say is decreasing uniformly, is less than area of P. So of Q, cross-sectional area of Q is less than that of P, which means that if they have the same volume as if Q and P have the same volume, then that would mean that this lack or this quantity which is less is compensated in the length. So length of Q would be greater than length of P. Now, since it is still a copper wire, resistivity is the same. So now we need to know the resistance. So if we write this over here, write RP, RQ, we have rho, LP, AP, LQ, and AQ. So resistivity is basically the same, so we can cancel it out. Let's say, for example, we are trying to find out the ratio. Now, AQ is less than AP, right? So this would mean that the 1 over AQ is greater than 1 over AP. Furthermore, the length of Q, my bad. Length of Q is greater than length of P. So that would mean that it's just adding on to this. So L of P. So this means that the resistance of Q would be greater than resistance of P. So we can say, since the average cross-sectional area of Q is lesser than that of P, it we can say it is compensated by a longer length. It is compensated, or volume is compensated volume is compensated by a longer length of Q. Therefore, uh, sorry, no, we first have to describe this relationship also. So since, sorry, resistance is proportional to length and inversely to area or cross-sectional area. So therefore, resistance of wire Q would be higher than that of P. Simple. On figure 6.3, sketch a graph of the variation of the average drift speed of the charge carriers with distance from end X of the wire Q. So this is wire Q. So at this end X over here, they have the same, same drift speed as over here. But what is changing? The cross-sectional area is changing. So V is inversely proportional to A. So yeah, so this means that as it comes across over here, the drift speed would increase because this is decreasing, this would increase. So this is what's happening over here. So simply this would be like this. This would be an increasing gradient because it is inversely proportional to A. So remember, this is not the same relationship as shown over here. We have to see what the picture for the wire Q is. All right, now the last question. An isolated stationary nucleus decays into nucleus R and the alpha particle. Alpha particle has speed 1.510 raised to power 7. Complete the equation for this decay. Okay. So for the alpha particle, proton number decreases by 2. So this becomes 86. And the nucleon number or mass number decreases by 4. So we would have 226. Right, okay. By considering momentum, calculate the speed of the nucleus R after decay. Okay. So we know that linear momentum is conserved in the nuclear decay, and they would be moving at opposite to each other. Also, since momentum before is 0, so momentum before is equal to momentum after. So this has 222 UMass and this has 4 UMass, atomic mass unit basically. So momentum before is 0, but momentum after, so both objects or both items are moving opposite to each other. So for example, if alpha we are taking it this one will be R. So alpha, so 4 u times by speed is given as 1.5, 10 raised to power 7. The other one would be 222u minus speed v, because we're trying to find out this speed. So this would be opposite to this alpha speed. So we have 4u equals, 4u 1.5, 10 raised to power 7 equals to 222u v. U cancels out. V would be equal to 4, 1.5, 10 raised to power 7 divided by 222. So 4 times by 1.5 divided by 2 times by 10 raised to power 7. So we get 2.7, 10 raised to power 5. State 3 quantities that are conserved during the decay. So they include, so again, it's the frequently examined questions: mass energy, total charge, number of nucleons, momentum, and these ones are the more important ones. So total mass energy, charge, nucleons. State 3 quantities that are conserved during the game. Momentum we have already discussed, so no need to talk about that. So total mass energy, total charge, and total number of nucleons. You could also add the total number of protons also, because nucleons does involve neutrons and protons, so you could say neutrons also. So that's it basically, and that's the final question. All right, so in case you have any confusions, any further questions, feel free to reach us out in the comments. If you feel that I made a mistake or if I wasn't able to explain question properly, do tag that time and please clearly state what your confusion is. And do check out those resources that we have been showing you. I showed you in the start of the class. We will give out the Patreon link also, and hopefully we will see you in the next video. Bye bye.